Good evening, everyone. So in this class, in the last class, we completed the chapter vectors, and in the last class, we discussed about the cross product of the vectors, and that was it with respect to the vectors. Now today in this class, we'll be starting with the kinematics portion, and particularly we'll be starting from chapter 3 of your NCERT. That's a motion along a straight line. And in this chapter, we'll be discussing some of the concepts related to position, distance, and displacement, and then we'll be discussing about the speed, particularly about the average speed and the average velocity, and then we'll move on to the instantaneous velocity and instantaneous speed, and then we'll be discussing about acceleration and average acceleration as well. So let's start with the position vector, distance, and displacement. Let's suppose this is our Cartesian coordinate system. This is the Cartesian coordinate system. This is our y-axis plane, and we know for motion, for any motion, the reference point is very important. We have to define a reference to study the motion of any particle, right? So in this case, since we are discussing the motion of a particle on a Cartesian coordinate system, for this case, we'll be choosing the origin of this Cartesian coordinate system as the reference point, right? So origin of this Cartesian coordinate system will be the reference point for us. And we'll be studying the motion of body, a general body, with respect to this reference, right? Let's suppose that generally, if we talk about the motion is of generally of two types. One is rectilinear motion, and another is what we call as curvilinear motion. The translational motion is of two types. One is rectilinear motion, and another we call as curvilinear motion. So rectilinear motion basically is that it's a motion along a straight line. It's a one-dimensional motion. Whenever particle is moving along a straight line, we say that particle is having a one-dimensional motion. It's moving along the one dimension, right? And similarly, for curvilinear motion, the particle can move along two-dimensional space, or it can move along in a three-dimensional space as well. That motion we call as curvilinear motion, right? So let's but in today's lecture we'll be discussing only about the rectilinear motion. It means the motion along a one dimension, right? So let's suppose that the particle, let's suppose that particle is moving along this path, along this curved path, right? Suppose that the particle, our particle A, was here at this position, right? Let's suppose at time ti, that's the initial time, our particle was at this position, and for this position, if we define the position of this particle, then we define the position of this particle as the position of a particle with respect to origin of this Cartesian coordinate system. And we know that the position of a particle is represented by the vector from the reference point, and here the reference point is our origin of this Cartesian coordinate system. So let's draw a vector from this point, that's the reference point, to this particle. So at time ti, that's the initial time, this is the position of this particle, right? So this is the position of this particle. Let's suppose that we denote this position of this particle with Ri. So this is the initial position of this particle, right? So at time ti, our particle was at position, it's moving along this curved path, and at time ti, the particle is having a position Ri. And Ri is nothing, it's the position vector. Position vector is nothing, is the position of a particle with respect to origin of a Cartesian coordinate system, right? Let's suppose that after time delta t, the particle is moving along this curved path, and particle reaches the point P, and it's reached point B after time t final. The time at which this particle reaches point B is Tf. We call this as a final time, right? So let's suppose that now the position vector of this particle has changed from the position Ri to some new position. Let's denote this position vector of this new position with this Rf. So the new position of this particle is given by this position vector. We call it as Rf vector, right? So this new position of this particle is given by this Rf vector, correct? Now the path length actually traveled by this particle from A to B. Let's suppose this path length is the delta S. This is the actual path length, right? This is the actual path length traveled by this particle, right? Actual path length. And this actual path length is traveled by this particle in the time delta t. That's nothing, that's Tf minus Ti, right? Tf minus Ti, correct? Tf minus Ti. Now, position vector is nothing, it's the position of a particle with respect to origin of a Cartesian coordinate system. It is represented by a vector. If we draw a vector from origin of this Cartesian system to the position of this to the point where the particle is located, then the position vector will be the position vector of that particle, right? So delta S is the actual path, right? And we know that Ri to Rf, the position of this particle has changed from Ri to Rf, and this vector from A to B, this vector from to A to B, this represents the displacement vector, right? So this vector here with the pink line here, it represents a displacement. It's nothing, it's a displacement. So displacement is nothing, it is final position vector minus initial position vector. We can also show that. Let's suppose that this forms a triangle OAB. In triangle OAB, right? In triangle OAB. In triangle OAB, if we use the triangle of vectors in this case, in triangle OAB, we know that Ri vector, and let's call this displacement vector as delta R. Let's call this as delta R vector, right? So this is nothing, this is the displacement vector, right? So this displacement is represented by delta R vector. And we know this delta R vector and Ri vector, they are taken in the same order, and the Rf vector is taken in the reverse order, and it is completing the triangle, right? So using the triangle of vectors, we can say that Ri vector plus this delta R vector will be equal to resultant of this vector, right? And the resultant of this vector is represented by Rf vector. So Ra vector plus delta R vector is equal to resultant. That's the Rf vector, that's the final position vector, right? So we can write here Ri vector is nothing, it's the initial position vector. And Rf vector is nothing, it's equal to final position vector, right? This is our final position vector. So from here, delta R vector, which is our displacement vector, it's nothing, that's equal to final position vector minus initial position vector, right? This represents our displacement vector, right? So this is nothing, this is our displacement vector, correct? So this is our displacement vector. So this represents our displacement vector, right? So it's nothing, displacement is nothing, it's the final position vector minus initial position vector, right? And the direction of this position vector, displacement vector, is towards the final point, from initial point to final point. We can clearly see in this diagram, in this Cartesian coordinate system, that the displacement vector is directed along the final point of this particle, right? From initial point to final point. So this will be the direction of this displacement vector, right? And one more point is that on this curve, we can see that this displacement or the length of this displacement vector, it's the shortest length between the initial point A and the final point B. Or we can say that displacement vector, displacement is nothing, it is the shortest distance. We can also say that displacement is nothing, it's the shortest distance between initial point and final point, right? Or initial position and final position. And we can also see that here in this case, the actual path length is the delta s, right? Delta is the actual path length, and we can clearly see that this delta s, which is the actual path length, it's usually greater than the displacement vector, right? And it will be only equal to this displacement vector when when the particle is moving along a straight line, and during that motion the particle does not reverse its direction or does not change the direction of its motion. So in general we can say that the actual path length is greater than the displacement, right? Or the length of the displacement, correct? So here this represents our displacement vector, correct? So displacement is nothing, is the final position vector and the initial position vector, and distance is nothing, is the actual path length, right? Distance is nothing. In this case, distance, that's equal to delta s. It's nothing, it's the actual path length. It's the actual path length traversed by a particle, right? The actual path length traversed by a particle, we call it as distance, right? Displacement is a vector quantity. We know that it's final position vector minus initial position vector. So of course it's a vector quantity, is directed towards the final point from the initial position, right? But the distance is not a vector quantity, it's a scalar quantity, right? It has no direction, it's just the actual path length traversed by a particle, right? So in general, the displacement is greater than the distance, right? Let's try to explore, let's try to learn about the average speed and the average velocity. So these are the two important concepts in mechanics, right? Average speed and the average velocity. So average speed, our average speed is defined as, it's nothing, it's total path length, total path length covered upon total time, right? So average speed is defined as total path length covered upon the total time. So in this case, if we look at this Cartesian coordinate system, I have denoted here that the total actual path length covered by this particle from point A to point B is nothing, that's equal to delta S. So delta S is our total path length here, right? So I can replace this total path length here in this case as delta S, and we know that this delta S path length was traveled in the time interval between t final and t initial, that's delta t, that's t final minus t initial. So we can replace it with delta t, or we can write it as delta s upon t final minus t initial, right? So this represents our average speed, while as average velocity is defined as, average velocity is defined as, average velocity is nothing, it's total displacement upon total time. Total displacement upon total time. The total displacement over total time, that gives us the average velocity, right? So it's nothing here. If we look at here, the total displacement is nothing. Total displacement is, that's delta r, delta r vector upon delta t, correct? So this represents nothing, it's the average speed, average velocity, right? Average velocity, correct? So in this case, if we try to find the direction of this average velocity is also a vector, right? The direction of this average velocity is given by the direction of this displacement vector, direction of delta r vector. So if we have to find the direction of average velocity, it's given by the direction of the displacement vector, right? So whatever be the direction of the displacement vector, same will be the direction of this average velocity, right? Let's suppose that if a particle is moving along a straight line, right? If a particle is moving on a straight line, the particle is moving along a straight path like this. It's moving along a straight path. It does not change its direction. So here in this case, suppose particle starts from A and it moves on, right, in this direction. So this is our particle, right? So particle moves along a straight line, along a straight line without changing its direction, right? Without changing its direction. Without changing its direction means that particle neither is moving right or left. It is not also reversing its direction also, right? So straight line without changing its direction, correct? Because if a particle is reversing its direction, it's still moving along a straight line, but now the direction has changed, right? Without changing its direction, correct? So in this case, what happens is that whatever be the total displacement, magnitude of the total displacement, same will be the magnitude of distance traveled, right? Let's suppose this particle moves from A to B. So from A to B, from A to B, this is the distance covered, right? So from A to B, whatever be the distance, let's suppose the delta is the path length covered by this particle from A to B, and same will be the magnitude of displacement also. In this case, we can say, therefore, in this case, we can say mode of displacement, that's equal to distance, right? That's equal to distance. It means that if a particle is going along a straight line without changing its direction, the important point is that particle should not change its or reverse its direction when it's going along a straight line. In that case, the displacement will be equal to distance, right? The magnitude of distance displacement will be equal to distance. That is, it means that at that time, v average velocity, right? Average velocity will be equal to the average speed, correct? Average velocity will be equal to average speed, right? Suppose that's the same particle is there, but it's once again moving along a straight line. The same particle is there, but it's moving along a straight line like this. It's moving along a line like this from A, right? So it starts from position A, it's moving along a straight line. But what happens is that after some time, let's suppose at point B, the particle reverses its direction. It reverses its direction and comes back, right? And stops at point C. It reverses its direction and comes back and stops at C, right? So here, uh, the magnitude of the total displacement will be equal to AC, right? And the total path length, that's the delta S, that will be equal to from A to B and then B to C. So AB plus BC will be the total path length, right? But displacement की अगर बात करें, or the displacement will be nothing, that will be that's the AC, right? That's AC only. So we can see here that the total here in this case, the distance is greater than displacement, right? Distance is greater than displacement. So in general, we can say that because here the particle was moving along a straight line, even if the particle was moving along a straight line, but it reversed its direction at some point, right? And in this case, what happens is that the total path length becomes greater than the displacement, magnitude of the displacement. So we can say that the displacement is less than the distance, or distance is greater than the displacement. Or in general, we can say average speed here is greater than v average speed. Here I am not using vector for speed, right? So it means I'm talking about the speed. So here I'm using a vector symbol for the velocity, right? So in this case, it will be greater, right? In this case, it will be greater because the actual path length is greater than the displacement, correct? So in general, we can say that distance in general is greater or equal to displacement, right? Distance can never be less than the displacement, right? In general, distance will be either greater or equal to displacement. And when it will be equal, it will be equal only when the particle is moving along a straight line without changing or reversing its direction, right? So similarly, we can say that average speed, average speed is greater or equal to the magnitude of the average velocity, right? In general, correct? So these are the two important points, right? So average speed in general is greater or equal to average velocity, or display distance is in general greater or equal to displacement, right? So let's move on to the next concept, that's about the instantaneous velocity and instantaneous speed, right? Let's suppose here in the previous case our delta t was equal to t final minus t initial, right? And let's suppose, let's redraw that diagram. So this was our Cartesian coordinate system here. This was our Cartesian coordinate system. So this is how our particle was moving along some path, right? Curvilinear path. And this is our origin of this Cartesian coordinate system, or we can say that this is our reference point, right? So let's suppose that this delta t approaches to 0, right? Correct. If this delta t approaches to 0, it means that in the previous diagram, if delta t approaches to 0, it means that the point P will coincide with point A. When delta t approaches to 0, it means that the point P will just coincide with the point A, or we can say that the chord AB here on this curve will become the tangent at point A, right? Will become the tangent at point A. So it means that if delta t tends to 0, it means that the points A and B are going to coincide. They are going to coincide here at this point. So this was our point A, that was Ti, right? And our point B is also going to coincide at this point, right? It's also going to just coincide at this point. If they just coincide at this point, now this chord AB will now become the tangent at this point A, right? It will become a tangent at this point A. Now this chord AB will become nothing. It will become tangent at this point A, correct? It will become tangent at point A. So this will be the tangent, right? So this is the tangent, right? Tangent at point A. And let's suppose at this point A, the particle is moving with a velocity v, right? So in this case, if the particle is moving with a velocity v here, in this case, our velocity will be defined as, that will be delta r upon delta t. But here in this case, our delta t is tending to 0, right? Delta t is tending to 0. And this position vector, the change in position vector, it will be very small. Our delta time t is nothing, it's an infinitesimal time, right? It is an infinitesimal time, correct? So if delta t tends to 0, it means that our v will be rewritten as, it is nothing, it's tr vector upon tt. So here it means that now this chord has just coincided the at point A, right? Now this chord has now become the tangent at point A, or we can say that our velocity here at this point now is nothing, it's dr vector upon dt vector, or we can say it's nothing, it's the first derivative of position vector. First derivative of position vector, correct? So it's first derivative of position vector at this point. So this is our first derivative of position vector, or we can say that velocity is defined as the rate of change of position vector, or the d by dt of the position vector, right? Rate of change of position vector with respect to time. And this velocity we call as Now here in this case, our delta time is infinitesimal. It's very small. It tends to zero. Or we can say that this velocity is nothing. It's the instantaneous velocity, right? We can say that this velocity is nothing. It's the instantaneous velocity. Correct? Instantaneous. Instantaneous velocity. And the direction of this velocity, in the previous case, the direction of the average velocity was the delta t was not tending to zero, right? Delta t was not tending to zero. It was a significant time interval, right? It was a very significant time interval. It was large time interval, right? But delta t tends to zero, the time interval reduced to very small, right? It almost tends to zero. But in this, there we defined the average velocity. But here, at this time, the position of the particle has changed by dr vector. So in this case, we define this velocity as instantaneous velocity because at this time, the time interval is very small and it is infinitesimal time interval which tends to zero, right? So we call this velocity as instantaneous velocity, correct? So the magnitude of this instantaneous velocity. So in this case, we can also say that the direction of this instantaneous velocity is nothing. Is the tangential to the curve at point A. The direction of this velocity is nothing. It is the tangent to this curve at point A, or at if the particle reaches at this point, right? At this point, the direction of this velocity vector will be nothing. It will be tangent like this, right? And at this point, the direction of this velocity vector will be nothing. It will be a tangent like this, correct? So this will be the direction of this velocity, right? So we can say that at this curve, at every instant, the direction of the velocity is changing, right? The direction is not same. The direction changes at every other instant. So the direction is given by the tangent on the curve at that point, right? So magnitude of this instantaneous velocity is nothing. We call it as speed of a particle, right? Speed of a particle, correct? Speed of a particle. Because here in this case, let's suppose if the particle was moving with the constant speed, the speed of this particle was not changing at all on this path. So we can say that the speed is here is constant, speed does not change, and the speed of that particle will be given by the magnitude of the magnitude of the velocity vector, and the direction of this velocity vector is changing continuously, and that direction will be given by the tangent at any point on this curve, right? Why do we say that the magnitude of the velocity vector gives the value of the speed at some particular time? Let's try to understand it, right? Why the magnitude of the velocity vector gives the speed, right? We know that instantaneous speed, I mean to say the magnitude of the instantaneous velocity gives the magnitude of the instantaneous speed, right? The speed here is instantaneous, right? It's not average speed. This is instantaneous speed, correct? Instantaneous speed. Now let's try to understand why the magnitude of the instantaneous speed, instantaneous velocity gives us the magnitude of the speed. Let's suppose that if we know that this displacement is for very infinitesimal time, that's very short time, right? It's very short time, correct? It's for a very short time in such a way that this delta t tends to zero, right? So we can see that in this time, the displacement will be a very short length, right? It will be a very short length as if it's a straight line for this time interval delta t, right? It's a straight line for this time interval delta t, correct? From here to here. So this is the dr vector here. If this is our dr vector, we can see that the actual length of the dr vector is the magnitude of this displacement vector, right? If the actual length of this dr vector is equal to magnitude of this displacement vector, so we can say that at this time the magnitude of the instantaneous velocity is nothing, is the magnitude of the speed, instantaneous speed at this time, right? So it means that here it's a straight line, correct? And we know that along when a particle moves along a straight line, the magnitude of the speed is nothing. It's the same as the magnitude of the velocity, right? So that's the reason why we calculate the magnitude of the instantaneous speed using the magnitude of instantaneous velocity, right? So we can write here magnitude of instantaneous speed is given by magnitude of velocity, right? Magnitude of velocity, correct? That's given by magnitude of velocity. So it was about instantaneous speed and instantaneous velocity. So our instantaneous speed is nothing. That's equal to dr vector upon dt. Or if we find the magnitude of the speed, that is the mod of v, that is modulus of dr vector upon dt, correct? So this represents our speed, right? This represents our speed. It represents the magnitude of velocity as well as the speed, right? So let's try to understand the next concept related to mechanics or the motion along a straight line. That's the acceleration, right? We know that acceleration is nothing whenever the velocity changes, right? It's the rate of change of velocity, right? We know that whenever a particle moves on a curvilinear path in 2 dimensions or 3 dimensions also, the velocity here in this case also, we can see that the direction of the velocity here is different at different points, right? It means the velocity is changing at different points. The velocity is not same at different points, right? Either the direction can change, the direction of velocity can change, or both the direction or magnitude of velocity can change, right? Direction can also change, magnitude can also change, right? Or both magnitude as well as direction can change, right? So we're defining here acceleration. Acceleration is nothing. Acceleration is defined as, it's nothing, it's the rate of change of velocity, right? It's the rate of change of velocity with respect to time. So this is nothing, it's the acceleration, right? So it means that how the acceleration is changing with respect to time. So rate of change of velocity, it's acceleration, or we can find the velocity mode of acceleration as mod of this dv vector upon dt, right? And we know that the velocity can change either by changing the direction or by changing the magnitude, or it can change by both magnitude and direction. Let's suppose that we have Cartesian coordinate system here. This is the Cartesian coordinate system. This is our y-x plane here, correct? Let's suppose this particle is moving along this curved path, right? Along this curved path, correct? We can see that let's suppose this particle was at this position here initially, and finally the particle is at this position, correct? And this is position B, and this is position A here, right? And let's suppose that the velocity of this particle at this point is along the tangent, right? Let me call this as V1 vector, and at P the velocity of this particle is along this, that's the V2 vector. Let's suppose that on this curvilinear path, both magnitude as well as both magnitude as well as direction of this particle are changing, right? Both magnitude as well as direction of this particle is changing. So then if direction is changing for this particle, then there will be some component of acceleration which will be responsible for the change in direction of this particle along this curvilinear path, right? If the direction, if the magnitude of the particle is changing, or if the magnitude of this velocity of particle is changing, or the speed of this particle is changing, then there will be a component of acceleration which will be changing the speed of this particle, right? So in general, we can say that there are always there are two components of acceleration here. One, which can change the speed of this particle, and second, which can change the direction of this particle. We can see that the particle is continuously bending like this. So it means that there must be some component, a component of acceleration which will be changing the direction of this particle, right? Let me call this as radial AR. I call it as radial component, right? And there must be another component of this acceleration which will be changing the speed of this particle, and that component of acceleration will be changing the speed of this particle along that tangent, right? Along that tangent, because the velocity of that particle along a path is given by the tangent, right? So this component will be changing velocity of this particle tangentially, right? So it means that in general there are two components of the velocity, two components of the acceleration. One component which can change the direction of this velocity, another component which can change the speed of this velocity, right? So there can be two components, right? One is the tangential and another is radial component, right? So what this AR does nothing. It changes the direction, right? Change the direction of a particle. Change the direction of a particle. So AR, I call it as a radial component. Which component? Radial, correct? Radial component. Change the direction of a particle, right? And what is this AT? This is the tangential component, right? This is the tangential acceleration, because what does this tangential acceleration do? This tangential acceleration change the speed of a particle tangentially, right? Change the speed of particle along a tangent, right? But this we call as tangential acceleration, and this we call as radial acceleration. So acceleration can be, if only magnitude of the if only the magnitude of velocity is changing, if only the magnitude of the velocity is changing, then we can say that the radial component is zero, right? Because the radial component is not changing any direction. If only the direction is changing, the tangential speed is not changing, or I mean to say that the speed of this particle is not changing, then we can say that there is no tangential component, right? The tangential component is zero, right? Okay, let's move forward, right? So our acceleration is nothing. So our acceleration is nothing. Our acceleration is nothing. It's defined as mod of acceleration is nothing. That's equal to dv vector upon dt, right? dv upon dt vector, right? Now let's try to understand what actually the average acceleration is. What actually the average acceleration is. So average acceleration is nothing. Average acceleration is defined as, it's nothing. It's the change in velocity vector, right? Change in velocity vector upon the time interval delta t, right? What does this represent? Change in velocity, right? Change in velocity. Change in velocity, correct? Between t1 and t2, right? So this is delta v vector, or we can say that its change in velocity is given by final velocity vector minus initial velocity vector upon the time interval t2 minus t1, right? T2 minus t1. So this is how we define the average acceleration, right? And the direction of this average acceleration is given by the direction of this change in velocity, right? So this will be p final vector minus p initial vector upon delta t, right? Let's suppose that this is our Cartesian coordinate system, right? This is our Cartesian coordinate system, and this is how the particle is moving along a curved path, right? This is how the particle is moving along a curved path. Let's suppose at here time t1, the particle was having some velocity v1 here, right? Velocity v1, correct? v1 vector. And after some time t2, the particle reaches here at point B. Initially, the particle was at point A. After time t2, the direction of this velocity vector has changed now. Maybe the magnitude of this velocity vector may have also changed, right? Let's call this velocity vector as v2 vector, correct? So this is our final vector. So between this time interval delta t, right? Between this time interval delta t, which is equal to t2 minus t1. If somebody will ask us what is the average acceleration, right? So our average acceleration will be nothing. Our average acceleration will be nothing. It will be equal to change in velocity vector, that's v2 vector minus v1 vector between the intervals t2 and t1, because t2 v1 is the velocity at t1 and t2 is the v2 is the velocity at t2, right? So we'll write it as t2 minus t1. So this will be our average acceleration, correct? So this will be our average acceleration. So in this today we discussed about the position, we discussed about the distance and displacement. And let's conclude all the points that we discussed today. First of all, we discussed about the position and then displacement and then distance also. And we made sure that reference is important for study of the motion, right? We have to take the point of reference, which is very important for the study of motion, right? For the study of kinematics or motion in a straight line or any other motion. The second point we discussed about the distance relation between distance and displacement. We saw that displacement is always greater or equal to displacement, right? Similarly, average speed is greater than all or equal to average average velocity, right? Then we discussed about the acceleration and instantaneous acceleration, also in instantaneous speed. Also, we also discussed that in a magnitude of the value of the instantaneous speed is given by the magnitude of the instantaneous velocity. And then we discussed about the acceleration, which is nothing, that's the rate of change of velocity with respect to time. It can have two components. One is the tangential component and another is the radial component. What does the tangential component do? It changes the tangential speed of a particle moving along some path. And similarly, what does the radial component do? It changes the direction of the velocity of a particle, right? Then we discussed about the average acceleration. Average acceleration is nothing. It's just the change in velocity between the two time intervals t2 and t1, right? Between the two times t2 and t1, or the time interval is delta t. T2 represents the v2 represents the time velocity at time t2, and v1 represents the velocity of a particle at time t1. So how do we calculate the average velocity? It's nothing, v2 minus v1 upon t2 minus t1, right? If we have to calculate the magnitude of this average velocity, that's nothing. That will be equal to, we'll just bring this time outside, right? We'll just calculate the mod of this v2 vector minus v1 vector and divide it by delta t time interval. We'll come to know about the magnitude of average acceleration. So that's it for today. In the next class, we'll be discussing problems or the questions related to all these concepts. Till then, take care and goodbye.